So here we have three different series, and what I would like you to do is pause this video and think about whether each of them converges or diverges. All right, now let's work on this together. So just as a refresher, converge means that even though you're summing up an infinite number of terms in all of these cases, if they converge, that means you actually get a finite value for that infinite sum, or that infinite number of terms being summed up, which I always find somewhat amazing. And diverging means that you're not going to get an actual finite value for the sum of all of the infinite terms. So how do we think about that? Well, we already know something about geometric series, and these look kind of like geometric series, so let's just remind ourselves what we already know. We know that a geometric series, the standard way of writing it is we're starting n equals, typical you'll often see n is equal to 0, but let's say we're starting at some constant, and then you're going to go to infinity of a times r to the n, where r is our common ratio. We've talked about that in depth in other videos. We know this is the standard way to write a geometric series. We know that if the absolute value of r is between 0 and 1, then this thing is going to converge. And if it doesn't, I'll just write it else, it will diverge. So maybe a good path would be, hey, can we rewrite these expressions that we're trying to take that are defining each of our terms as we increment n? If we can rewrite it in this form, then we can identify the common ratio and think about whether it converges or diverges. So I'm going to focus on this part right over here and see if I can rewrite that. So let's see. Can I rewrite, let's see, 5 to the n minus 1, I can rewrite that as 5 to the n times 5 to the negative 1, and then that's going to be times 9/10 to the n. And let's see, this is going to be equal to, I could just write this as this part right over here. I'll write as 1/5, that's the same thing as 5 to the negative 1, times, and then 5 to the n and 9/10 to the n. Well, I have the same exponent, so I can rewrite that as, and we're multiplying all this stuff, I'm just switching the order. This is the same thing as 5 times 9/10 to the nth power. And so this is going to be equal to 1/5 times, well, 5 times 9 is 45, divided by 10 is going to be 4.5. So times 4.5 to the nth power. So that original series I could rewrite as, just for good measure, I'm starting at n equals 2. I'm going to infinity, and this can be rewritten as 1/5 times 4.5 to the n. So what's our common ratio? What's our r here? Well, you can see very clearly it is 4.5. The absolute value of 4.5 is clearly not between 0 and 1. So this is a situation where we are going to diverge. Now, if you found that inspiring, and if you weren't able to do it the first time I asked you to pause the video, try to pause the video again and try to work these out now that you've seen an example. All right, let's jump into it. So I'm just going to try to algebraically manipulate this part to get it into this form. So let's do that. So I could rewrite this. Let's see if I could get some things just to the nth power. So I could rewrite it as 3/2 to the nth power. And I could write this part right over here as times 1/9 to the nth times 9 squared. This is going to be equal to 3/2 to the n. And let's see, I could factor out or bring out the 1/9 squared. So let me do that. So I'll write that as 1/81. I'll write it out there. So that's this part right over there. 181 times 3/2 to the n times 1/9 to the n. But 1/9 to the n, that is the same thing as 1/9, all of that to the nth power. And the reason why I did that is now I have both of these things to the nth power, and I can do just what I did over here before. So this is all going to be equal to 1/81 times 3/2 times 1/9 to the nth power. These are just exponent properties that I am applying right over here. And so this is going to be equal to 1/81 times, let's see, 3/2 times 1/9 is 3/18, which is the same thing as 1/6, times 1/6 to the nth power. Or if I were to rewrite the original series, it's the sum from n equals 5 to infinity of now I can rewrite it as 1 over 81 times 1/6 to the nth power. This is our common ratio, 1/6, very clearly. I'll do that in this light blue color, 1/6. That absolute value is clearly between 0 and 1. So this is a situation where we will converge. Converge. Now let's do this last example. I'll do this one a little bit faster. So let's see. I could, if I'm just trying to algebraically manipulate that part there, that's going to be the same thing as 2 to the nth power times 1 over 3 to the n times 3 to the negative 1. Well, this is going to be the same thing as 2 to the n times 1 over, why did I write equals? Times 1 over 3 to the n. And 1 over 3 to the negative 1, that's the same thing as 1 over 1/3. That's just going to be equal to 3 times 3. Well, that's going to be equal to, I'll give myself some space, so I'll start out here. That's equal to, I'll put the 3 out front, 3 times 2 to the n times, and 1 over 3 to the n is the same thing as 1/3 to the nth power. And so this is going to be equal to 3 times 2 times 1/3, all of that to the nth power. And so that's going to be equal to 3 times 2/3 to the nth power. So we've just simplified this part right over here to 3 times 2/3 to the nth power. We can see that our common ratio is 2/3. So the absolute value of 2/3 is clearly between 0 and 1. So once again, we are going to converge. Converge. And we're done.